Okay, I think the live stream is started. Yeah. So I guess I'll start now since everybody who.
Just one moment.
Yeah. Okay. Sure.
Yeah, you can start now. You've started the recording, so you can start now.
Yeah. Okay. So yeah. So let me start my screen sharing. Right. Can everyone see the screen?
Yes.
Okay. So I'll close the chat window. Um, so yeah, people won't be able to see me chat if won't be able to see anyone chatting if anyone writes there. Just saying that. Okay. So okay, in this what we want to talk about today is essentially some optimizations to the PDR algorithm and some things that to keep in mind in general how to go about implementing it. So this is mainly like there are several different papers talking about implementation of PDR algorithms and like PDR being a really sort of industry leading algorithm in this field. There are many people who have tried different variants of it and different flavors of implementation and so on. So this particular things that I am talking about is taken from this paper. So uh, this paper over here, you can see the title, right? I'll share this paper with you guys as well. So um, this paper actually talks about a lot of different things, and it goes into a lot of detail about how exactly they're implementing, and they do a lot of experiments to see what works and what doesn't. So we'll not go into all of that. I'll only take like two things, essentially three things from this paper, and speak about that in terms of implementation. And that is what basically we'll ask you guys to sort of follow when you're implementing this. So this will be a joint project, so three of you can sort of collaborate together and distribute the load. So I think with the three sort of optimizations from this paper, implementing this entire thing is going to be a sufficient amount of work for three people. So yeah, so if you remember, this was the
just one interjection. I guess you might notice the PDR for its popularity. It's a fairly recent one. It's only like 10 years old. Okay.
yeah
Um,
yeah and it is sort of groundbreaking when it came out, right, as far as I
Yes.
understand. Yeah.
Correct. Yes.
So which is why it came into popularity very quickly. Yeah. There is still like active research with PDR implementation, right?
I think so. Well, yeah, with PDR, combining that with, by the way, predicate abstraction,
Right.
and so on. And Wednesday, Madhukar, we'll have a guest lecture. Okay, and he'll be talking about predicate abstraction and counter example, CGAR, counter example guided abstraction refinement. So I think these two, that plus this PDR like things, I mean, people are combining these things, extending it to several other theories and so on. So these are the kind of state-of-the-art research that's going on in scaling model shaking, I would say. Yeah, go ahead, please.
Right. Yeah. So just as a reminder, should I go over the pseudocode ones, or do you guys remember most of the things from Friday's lectures? Yes, no, anything.
Yeah.
No.
Yeah. Okay.
Okay, I'll go over it one side. Okay. So the PDR algorithm basically what it has is it's got a number of frames. So you have, say, your init is this, and say your safe region, the actual safe region that you want to prove is covered within the reachability, or let's say that you want to prove that this unsafe region is not reachable from the init. That is the red one here. So the frames are basically going to be over approximations of the reachable regions of the init, right? So maybe the reachable region from the init looks like in n steps looks something like this, right? So let's draw three steps, I guess. So this is the first step, then maybe you have the second step, and then maybe you have the third step, right? So this is, say, your reachable region from the init, and then the PDR algorithm, what it will basically have is over approximations of this. So the 0th frame, let's say, the 0th frame is the same as the init, so that is F0. The first frame that you'll have is going to be an over approximation of all the things that are reachable from the init in one step. So it will have everything that is reachable in one step and maybe something more. So that's the blue one. So that's F1. And then F2 will similarly have everything reachable in 2 steps and maybe something more. So that this is sort of what's F2. So this is the idea, and you'll have F3 and so on. So now I'm not going to keep these the black squares with me anymore, and the reason is because we're not going to think about the actual non-over approximate the exact reachable sets. So we're going to only work with these over approximate frames, right? So PDR maintains these frames, and the idea is the idea and the hope of PDR is that at some point maybe we'll be able to find either a counterexample, or we'll be able to find 2 frames which are exactly the same, right? So we sort of keep propagating these frames, and we keep refining these frames until either we find a counterexample or we find 2 frames which are exactly the same. So that is the central idea of the PDR algorithm. And the way we do this is that we basically, whenever we add a new frame, what we do is we initially keep the frame as everything other than the unsafe region. So that is essentially the property that you want to check as the frame. So your frame is going to be, say, something like this, right? Everything other than the unsafe region. And then you see that, is there any point over here that in one step goes into the unsafe region, right? So if it does go into the unsafe region in one step, then you remove this point from your frame. So your frame now becomes this. And you backwards propagate it, right? So by backwards propagating it, I mean that you check for the same thing for the other frames as well. So now that your frame is not the entirety of the not your entire property, you need to now check that anything from your previous frame. So remember, one of the invariants of these frames was that anything in Fi, like the one step image of Fi, should be in Fi plus 1, right? So if you have F1 suppose over here, and this is our F2, then everything in F1 should, under one step image, go to something inside F2 itself. It cannot go outside of F2, right? So now that we have removed this black point, this black point that we have removed, it could have been that this black point had actually come from some point over here, right? So there was some point here that in one step had gone to this black point, that goes to this black point, right? So now that we've removed this, to maintain our invariant, we need to remove this previous point from F1 as well, right? So we do that. So again, our F1 will then become, so we'll basically remove this point from F1 as well. So our F1 then becomes something like this, correct? And then we go back again and again. So in general, I've shown this for 2 frames, but in general, there can be n frames, and you keep going back like this, removing your points and so on, right? And you have to do this removal process recursively, because there can be other points from this this point as well that also in F1 that also lands over here, right? So then you have to recursively remove this one as well. So your F1 then gets rid of this one, and so on, right? So you'll have to do all of this. And in this entire backtracking or removing this counterexample to inclusion process, if at some point you see that, okay, you have a point in F1 that you've just removed, and you see that, okay, there is a point in F0 that goes here. So now this actually gives you a counterexample path, right? So if at some point while removing and backtracking like this, you end up going into your init, then you know that you have found a counterexample. Otherwise, you recursively keep removing it, and in that process, you're in some sense refining your frames. And once you have done with this entire refinement, then you check whether 2 frames are equal or not, right? Because it might happen that, when you've refined this point, it ends up happening that F2 is equal to F1, right? So let's say that we don't have this counterexample path and we have removed all of these points. And let's say that although the picture looks like this, there is actually no more points over here, right? There are no other points here. So then what ends up happening is that F2 is equal to F1, and then you found an inductive invariant, right? Because anything that is in the one-step image of F1 is inside F2, we know, but F2 is equal to F1. So that means that anything in the one-step image of F1 is actually just F1, right? So F1 contains everything that is reachable in n steps or in some number of steps from the init. And the one-step image of F1 is inside F1 itself. So that means that we have actually found an inductive invariant, or F1 is an over approximation to an inductive invariant, which means it is an inductive invariant in some sense.
Yeah, only one small thing, that in addition to checking reachability of F0, that black spot itself can be an F0. Okay, so the check has to be made.
Yes, yes,
Yeah.
definitely.
So
yeah.
not only reachable, I mean, because F0 is not an over approximation, exactly the same thing.
Yeah.
Therefore, yeah, you also need to check that either it is reachable or is unreachable, or it's not in there. Go ahead.
Right, exactly.
I think it is very good. It's a very good way of describing. Yeah, especially you showed two things, okay, that could go from F1 into the same thing as well. Yeah.
Yeah.
Yes.
And in fact, that's where the sort of the optimizations will come in.
Correct.
Yeah.
So
this is the
last point you said.
Go on. Okay, I couldn't hear you. Sorry.
Could you repeat the last point that you just said?
Right. So what my last point was basically that suppose that now after this stage of refinement, we actually see that F1 is equal to F2. I mean, in the picture, this sort of looks weird, but let's imagine that all of this space is empty, right? Like there are no points here in some sense. So if F1 equal to F2 sort of happens, then we have proved that our red region is unreachable, right? Because F1 equal to F2 means that F1 or equivalently F2 is actually an inductive invariant, right?
That I get. The last point, sir.
All right. Okay. Yeah.
Go ahead if you want to explain.
Yeah. So I'll maybe draw another picture. So let's say that this also can happen, right? So let's say that you have your black region, red region, and you have say two frames, frame 1, and you have added a new frame 2. And when you're looking for a point inside F2 that is that goes to something inside the red region, you might end up with a point like this as well, right? This can also happen, correct?
Yeah.
So your point can be as far back. In fact, it can be back into F0, right? So it makes sense for us to do an early check to see that the point that we have got, the CTI, the counterexample 2 inclusion that we have got, is that actually inside the init region, right? Because I mean, why wait until we get to F0? So if we follow this previous method, we'll still find a counterexample path in the sense that we could still keep checking inside here. But the idea is that you could actually hit the F0 somewhere earlier, like in F2 itself. When you're checking for points in F2 itself, you could already hit F0, right? So you have to.
And that's because the critical point is F0 is not an over approximation. Every frame is an over approximation of things that are reachable in up to I steps. Okay, whereas F0 just has those things, and therefore F0 can have states that are reachable directly. Okay, so that's
So there can be like some points in F0 that ends up in red in one step, and you can find that as a CTI for F2, right?
Yeah. Okay.
So this is the point that this is a crucial check that we'll have to do, the check whether this black point is in F0 or not. So essentially two steps. One is check in F0, and then the second one would be to actually block and so on. Right. So this is the overview of the algorithm. Now let's look at the pseudocode, and I mean the reason why I want to look at the pseudocode in some details is because I'll be hopefully writing some a little less formal pseudocode than this, but still some pseudocode. So there's this main function, and as you can see there's a while loop that is going on that's doing two things, right? So extend frontier, what that basically means is that we're adding a new frame. So remember that this refinement, this blocking thing that we're doing recursively. We'll do it until we cannot do it anymore, right? Until we cannot find any CTIs anymore. And at that point, if we haven't proved or found any counterexample path, then all we can do is add another frame, right? So that's what the extend frontier is going to do. Then so then the extend frontier actually also takes care of this this recursive blocking and refinement. So if you look at the extend frontier procedure over here, this is actually once it has found, like once it has set this fk plus 1, it is actually going to look for states that from fk go to something that is not inside fk plus 1, and it's going to block it, and it's going to remove these states recursively, right? So this while loop actually iterates over all the points in in the last frame that you've added that in one step goes into your red thing. And for each one of those points, you're calling this recursive procedure remove CTI, which is going to recursively remove those points, right? Once you've done with this, so once this extend frontier procedure is finished, you've essentially come to a point where you have your like you have removed all the counterexamples to inclusions in your frame. So then what you do is you do the propagate clauses, right? So the propagate clauses, what that does is essentially looks for relatively inductive parts of your clauses. So if you remember, all your frames are CNF formulas, right? So all your frames essentially look like intersections of clauses. So every fi is going to be some ci0 and ci1 and so on to some cik, let's say, right? So if I draw a picture, this sort of looks like this, right? So this is your ci0, ci1, sorry, ci0, ci1, and so on. And you may have a situation where essentially you see that one of your clauses or say your CI is such that anything that is inside FI under one step always remains inside CI0. So it might happen, so for example, that your FI say some small region inside this intersection CI0, CI1, maybe there's like 3 clauses. So CI0, CI1, CI2, right? So I think I'm writing all of them as CI0. I'm sorry about that. So there are 3 clauses, CI0, CI1, CI2, and your F is this tiny intersection over here. And what you see is that any state inside here in one step always remains inside CI0. That might happen. Now, when this does happen, what you can immediately say is that, okay, if we have already reached a point where anything inside our frame, like right now in one step, is going to remain inside CI0, we know that CI0 we can AND the next frame with CI0, right? Because anything inside our frame in one step is going to remain inside CI0. So whatever our frame is in the next step, we know that all the points there is going to be inside CI0, correct? Because I mean, or in the sense that all the points in the image of this particular frame inside our next frame is going to be inside CI0. So our next frame might be something like this, right? But our image of this previous frame, so this is our fi, this is our fi plus 1, and the image of our fi, we know that it is going to lie inside CI0, right? So fi plus 1 is an over approximation of this image of fi, and we always want to keep sort of a reasonably refined versions of our frames, right? So we can safely, or rather we can say that we can soundly refine fi plus 1 by ANDing CI0 with it, right? So if I AND CI0, then we know that we are not going to lose any behavior, right? Because all the things in fi under one step is going to stay inside CI0. So we know that in fi plus 1, any point that is here in this region, in some sense, is fi plus 1, is actually not going to be reachable from fi, right? So we can safely AND it with CI0, and we'll get this ANDed region with CI0 as the new fi plus 1. So we can sort of refine fi plus 1 by ANDing it with CI0. So this is what the propagate clauses thing does. So it goes from the first frame onwards, and it looks for such clauses such that anything inside fi in one step remains in such clauses. These are called relatively inductive clauses. So ci0 in this example is relatively inductive, and it will and everything in the future with the relatively inductive clauses, right? So it'll and fi plus 1 with relatively inductive clauses in fi, and then it'll look for relatively inductive clauses in fi plus 1 and fi plus 2 with it, and so on, right? So this is another step of refinement that we do here. And the hope is that after these, so both of these sort of refined, right? This adds a frame and then refines via removing CTIs, which is necessary for soundness. So, or maintaining the invariance. So after this ends, we are maintaining all the invariance for the frames, but we can actually sort of do better, and we can do this extra step of refinement, which is called the propagate clauses. And this is not some optimization. This was, as far as I understand, it was a part of the original algorithm as well. So propagate clauses is essential to this algorithm. And
well, essential in the sense, I'm not so sure. So that's actually, there is one thing that I've been giving you as an kind of, I said,
I see.
I'm making 3 problems for them to work on, like a take-home thing, to enhance their thing. I think that this is not essential for termination. Okay.
Yeah. But
it causes termination faster. Okay.
Right. Yeah. So what I meant was like in the sense that it was a part of the original presentation of this algorithm, right?
It was correct.
Yeah. So that is like it is something.
It was not an
canonical.
It's an afterthought or something. So that was actually a very astute and insight. Okay.
Right.
That the original authors of the algorithm, Adam Bradley,
Yeah.
Otherwise, it would probably not have been as efficient. Okay.
Yeah. So
yeah. See, one thing, that's what. So you can see that if some fi itself is an inductive invariant, then what will have to happen is every clause has to be relatively inductive, because then every state, which is at the intersection of all the clauses, will fold into itself. Okay.
Right.
So what's happening is, this is kind of a new information that you've learned. Although I have not reached full inductiveness, I know that the image is always going, one-step image is always going to be here. And since you want to have the next one only as an over approximation, you might as well do that. So, but there might be still some things in here which are making, inside that relatively inductive clause, which are still, CTIs, okay? Potential CTIs that will be discovered only later on, okay? Because they take longer steps, and therefore they may need refinement later on. But now, at least you know that, okay, it is safe to just keep your FIs within this CI. Okay?
Right. So that picture would look something like you have a red region here, and maybe this is your one point that in one step goes from your FI and stays inside CI0, but it goes inside your FI plus 1 in one more step. So this one will be discovered as a CTI for FI plus 1 eventually, and will be removed. But for now, we can, at least safely define FI plus 1 to the blue region intersection with CI0, right? Yeah.
Correct. Yeah.
So yes, that is what the propagate clauses does, and the pseudocode for propagate clauses is given at the end. We're not going to look into this in too much detail. I mean, you can read the pseudocode later on. We're not going to provide any optimizations here. So the main thing that will be optimized is this remove CTI procedure. So before I go into this, does everyone at least intuitively understand what the algorithm is doing, and specifically this recursively blocking thing, because that's where the optimizations I'll show the optimizations. Any questions so far? Especially primarily because
I have one thing.
Yeah, go on.
So we compute the over approximation F1 right from F0. So F1 might also contain states which are not reachable from F0, right?
Yes.
Okay.
Yeah. So that is what we mean by over approximations. Yeah.
Yeah. So it's always okay to keep in those kinds of things that are not reachable in your over approximation, as long as they are not counterexample to induction. Okay. I mean, when you keep them, as long as they may not be reachable from an initial state, but they should not get you outside into a not P, into a bad state. That's all. Yeah.
Okay.
Yeah. So are there any further, or should I go into the details of the remove CTI and optimizations? Okay.
Yeah,
so,
you can continue.
Yeah. So I'll go. So this is the remove CTI pseudocode over here. Now this, okay, so before we do anything, this pseudocode is in some sense doing something recursively, right? So the way I talked about this is to get one point in fi or f2, let's say, that is a CTI, and then recursively, like for all the CTIs for coming to this point from f1, we'll block them, and for them again recursively we'll block all the CTIs coming from any previous frames and so on. So this is what the remove CTI algorithm is written to do recursively, right? So if we go over this algorithm, the first thing that it's doing is it's checking whether or not it is intersecting with the initial one, right? So S is your this point that we are trying to check. So we'll call, when we call remove CTI for a particular point, we pass it the point, we pass it which frame we want to check for, and so on. So, and of course the model, which is always going to be passed to everything. So we pass it the point and the frame number. So S is this point, and we're checking whether that is intersecting with S naught, which is the initial. If it is, then we can abort with saying that we have found a counterexample, right? Otherwise, what we'll do is we'll do the remove CTI check. And as sir mentioned last time, it is sound to actually add this not S in. I mean, if you just have Fi, R, and S prime, that is actually sufficient for a remove CTI check. But it's sound to add this not S in because you'll be removing the S anyways, right? So it is okay to look for things that are outside of S that reach here. Because if there's something, if S itself is like a self loop or something in S reaches into S itself in this frame, that is fine because we'll be removing S anyway, right? So yeah, so this is our reachability SAT check. And again, we'll not be changing this SAT check. The SAT check remains the same. It's only what we do before and after the SAT check in some sense that will change. Fundamentally, we will not change the SAT check, right? So for then so this while loop again is iterating over all the models we can get from the SAT check. So that is that basically corresponds to this can be a model from the SAT check, this can be a model from the SAT check. So we are sort of looking at everything that can send arrows into this particular point, right? And then what do we do is for L from 0 to I, what we do is essentially we'll be basically blocking this not S from everything from 0 to I. So over here, we saw that we blocked this not S in F2, right? But essentially what this pseudocode shows is that, okay, we'll also block, so this is our S, let's say, we'll also block this S. Okay, let me just copy this picture instead of going back and forth. So yeah. So instead of, saying that we'll block it just in F2, we're also going to block it in F1 as well. And the reason is that, this S could have also been in F1, right? F1 could have been something that also contained S, something like this, right? So we'd have to block it in F1 in that scenario as well. So essentially what we do is we just block it in all frames from 0 to I, right? And then we extract the predecessor of S from the SAT instance. So that is being said as T over here. So T in our diagram basically looks at this point. So this will be a T, this will be a T in different instances of the while loop, and we recursively do remove CTI. So the first thing that I would like, okay, maybe I can talk about that a little bit later. But the one thing that is probably clear is that this remove CTI doesn't necessarily need to be recursive, in the sense that you can as easily rewrite this code to just use some a queue, right? So I would like to sort of do that first. So that would be, so that remove CTI would look something like this. You do the same, like you basically extract an S from the queue instead of having an S from your argument. So you take, say that S comma I, you have popped it from a queue, right? And this queue can be a priority queue, which pops things with lower I's before things with higher I's, right? So queue is a priority queue over I. And it has these SI pairs, right? So we pop an SI pair from queue, and then we do these two things. We do the inclusion in S not check, and we do this check, right? The CTI sat check, right? So then now notice that this CTI sat check goes on in a while loop, right? So we can do a CTI sat check in a while loop. And what we can do is we do these similar things for this as well. So inside the for loop, we do the, okay, so I should probably move this to keep the indentation sort of, right? Yeah. So inside that, we do the similar for loop. So we go for L from 0 to I, FL is equal to FL and not S. And we get the T from the sat instance. And now instead of adding, like calling remove CTI recursively again, all we need to do is we'll have to add this thing to the queue, right? So we say that we're going to push this pair T comma I minus 1 into the queue, right? This works. So this is just sort of a reframing of this particular recursive procedure as a non-recursive procedure. And the reason I'm writing this as a reframed version of for the non-recursive procedure is because this will basically help us in seeing some of the optimizations, or this will basically be how you'll have to rewrite this remove CTI when you introduce some of the optimizations. So I'm just going to write it over here, right? So now let's look at some of the optimizations that we can do. So for that, again, I'll copy this and go to the next slide. So yeah, so the first optimization that sort of comes to our mind is this. You see here that we had sort of two T's that we could get, right? So T1 and T2. So in some sense, we are, it is also possible that for the same S, there can be various different T's in the previous frame that we'll have to block, right? And right now, S, T are just states. And I mean, I'm probably like teasing this already, but because I'm saying right now, soon they'll not be just states, right? But yeah, so if you have one single state S in this procedure that we are actually recursively going over all the states, various TIs that could be in the previous frame that can go to S in this frame, right? And there can be many such states, right? Because you can have a picture where you have like a large number of points. So you can have, again, this, and you say you have your two frames. Maybe. Right, and you have this sort of a situation. This is your S. This is going inside your red region. And you can have a large number of points in your in the previous frame, right? So maybe let me draw this a little bit bigger in fact. So you can have, say, these many points, right? Some huge number of points, and all of them go to your S in a one step. And if you think about it, really, you're working with SAT formulas and potentially exponentially large models. This is not a very uncommon scenario to imagine, right? So the worst, like in the worst case scenario, this entire recursive procedure might end up happening exponentially. Well, to be fair, we cannot really guarantee that we will not be exponentially keep doing this thing, but we can at least say that, is there some way in which we can, instead of blocking one state at a time, we can block a number of states together, right? So here, for example, all of these points go to S in one step, right? So if we could, let's say, instead of dealing with all of these points as individual states, if we could find some formula that captures the set of points, right? If we could, instead of having these each individual t's, if we could find some t prime, which now is not a state but a formula or a predicate, let's say, that captures.
I think.
Yeah.
I'm sorry. Can you hear me?
Yeah, I can hear you. Go on.
Okay. See, if it's a single state, then it is represented by a cube that has all the state variables. Okay, a fully defined single state. Okay, actually, a single state is characterized by a cube. A cube meaning conjunction of literals.
Right.
That has all the literals. I mean, that has all the variables. Okay, that encode that are used in the encoding of the state. Okay, this is what I call a state bits. Now, if that cube itself can be a generalization in the sense, I mean, it can denote multiple states if it does not include all the variables. Okay. So that is also a general, so if for example, the red state here, which is a single state, if you drop some of the literals and still it satisfies not P, that is also called a generalization. Okay, so it means now you have a cube can also be denoting more than one state. Okay, if you're able to drop the thing, that is one. And what right now, and even further generalization, I guess, is that it means that multiple thing, it can have multiple clauses also. Okay. Since we are restricting ourselves to CNF form, it can have clauses that do not have. Okay, there is negation of cubes derived from cubes that do not have all the literals variables, or it can have multiple clauses also. Okay.
So
So
that is a really good point. So in fact, so we'll look into what specific ways we can generalize these things in a bit, but the essential idea is that we want to, so if you think about it, a single state, as sir said, is captured by just a cube over all the variables, right? So cube over all the variables looks something like, so if you have 4 variables, say x0, x1, x2, x3, then a cube over all the variables would something like x0 and maybe not x1 and not x2 and x3 corresponding to the state. So this is basically refers to this particular state where you have 1, 0, 0, 1, right? For x0, x1, x2, and x3 respectively. So your states are actually given by these sort of formulas, which are cubes over all the variables. And sir said if we can drop one of these variables, like the formula that we get for in that case is something that will talk about multiple states, right? And that is essentially a predicate, and that is one way of generalizing, and that is in fact the way of generalizing that we'll look at. So essentially what we're looking for are formulas that will sort of give you more than one state in this side that all lead to your S. Right?
Okay. And a related point that I want to make is, I mean, like you said, like what he has, Diganta has shown, there are multiple points here on the left side that are predecessors that are all going to the same state. Technically, you can compute that whole thing. That is doing the existential quantification. Okay. Right. One-step existential quantification. Now, you could do that in every step, okay, and then get all the states that all the predecessors that go into one state, or if that one state itself is a set of states, it is like one-step existential quantification elimination. Okay, now. But that is something that you don't want to do, because I mean the whole procedure here was not to do existential quantification. Remember that how we came from the BDD thing to SAT, okay, in order to really not do existential quantification in each step, okay, And although it's only one step, it is not as bad as doing existential quantification over multiple steps. But then if you keep doing this in every step, it's as good. Okay. So I guess generalization, we have to look for generalization which are inexpensive. Okay. And but they may not get you all of it. Okay. So what are those things?
Yeah, exactly. So yeah, so just as I said, you can actually do an existential quantification and find this exact predicate that we're looking for. But we want to sort of hit a balance between not doing any generalizations at all and doing such generalizations that are itself very difficult to compute, right? And in general, once you get, even if you can, do a fast existential quantification, that will probably give you a lot of clauses at the end that you'll have to block off, right? Excuse me. So like if you imagine the situation where you have no generalization, what you're having to do is you're having to block a lot of clauses in F1, right? So your F1 was previously something, and now what you're saying is okay, we'll have F1 and not T1 and not T2 and not T3, right? And so on. If you do an existential quantification, you might end up with a similar situation where you're not doing it in different steps, but you have some huge multiple clause formula that you've gotten from an existential quantification after spending a lot of time doing that existential quantification that you're still having to block. And that is still some huge formula, which is say some C1 and C2 and C3 and so on, right? So both these extremes, in some sense, both not doing any generalization and doing full generalization, we expect them to not be very optimal. So we want to find some balance between them, some generalization that is fast, but that will still hopefully reduce the number of clauses that we're having to block in FI at each step, so that we can quickly finish the steps and hopefully get a earlier termination faster, right? So this, and I mean, as you can imagine, there can be various different such generalizations and various different points of balance that you can pick. But what we are going to refer to is again what this paper talks about. So so what they do is something that is called ternary, that they call ternary. Yeah, go on. Hello?
Oh, no. Momentarily somehow. Can you hear me?
Yeah.
Momentarily there was silence, and that's why I thought maybe there was a technical issue. Okay. Go ahead.
Yeah. So yeah, in the paper, what they do is what they call this ternary simulation, right? So before I go into the details, any questions so far as to why we want to do a generalization and what the general idea of a generalization is? Yes, no? Any questions?
No questions.
No questions.
Hello?
Yeah, they said no questions.
Okay. Yeah. So yeah, so let's look at some of the details of the ternary simulation. So what ternary simulation does is essentially this. Once you do this CTI SAT check here, right, what you would get is some S and T that has this property, right? So T is in your, so you get an T, which is some huge cube like this, some full cube like this, that is in Fi minus 1, and you have an S, you had your S in Fi, and you have some S and T such that T goes to S, right? So that is to say the R of, so R is basically the transition relation that I'm using. So R of T comma S is true, right? So you have already a T like this. What ternary simulation will try to find is whether you can, like Sir said exactly, whether you can drop some variables in the T completely, right? So in ternary simulation, you sort of have three constants. So you have 0, 1 that we used to have before, and you have this star. You may have seen this while extracting satisfying instances of BDDs using CODD. The star basically means that this particular variable can take whatever value. So you're trying to see that, okay, can we replace any variables in T with star and still have this to hold, right? So to do this, what we do is basically, firstly, we'll have to specify the rules of ternary simulation. And the rules is this, is that, so star and 0 is 0. Star or 0 is star. Star or 1 is 1, and star and 1 is star, right? So this sort of makes sense, right? I mean, and it sounds from the perspective that you can replace star with 0 or 1, and if you do it uniformly if you replace the same star with the same thing in each formula, then it should hold, right? So
one quick question.
Yeah.
So we are going to check this for each individual case, right?
Each individual?
For each individual, like for T1, T2, for all the T's, right? In each
Yeah. In some sense, we are going to do it for each individual case, but the hope is that we'll have fewer cases once we start eliminating more T's.
So another one quick question on generalization. So in any case, generalization would be better than the above method, right? And in the above method, we explicitly mentioned each state T1, T2, T3.
Yeah.
So generalization, generalization consists of CNF clauses. Right?
So you might actually do a generalization that gives you a huge clause for this black region, right?
Okay.
So you might get some huge formula for this with a number of different CNF clauses. I mean, ultimately you'll have to find some formula. Whatever formula you'll find will be in CNF clauses, because that's our predicate representation, right?
Okay.
But if it is some huge formula that you get for this block, then the benefits of generalization actually go away, because you'll have to do a lot of work potentially to reach that formula. And in any case, you're having to block a lot of things in F1 in any case, because you're having to add this huge formula in.
Okay. I get it.
Yeah. So the reason why we want to keep the number of clauses in these FI is less is that A, it makes SAT checks faster always, and B is that we are actually working with these clauses in other steps as well, right? For example, this the propagate clauses, we're actually iterating over clauses.
Yeah, but there was only one small point. I mean, you finish. Yeah. Okay, so I mean, no. I mean, if you do, see, I'm not saying that you're doing it. Yeah, Diganta, you're right. Okay, that when you get into huge clauses, this kind of generalization, extending it, how you extend it is also a question. Okay.
Yeah.
But you could probably, I mean, even this conceptually, you can do this ternary simulation for the entire formula with clauses. No, so you could. I mean, but you have to be careful. Okay, so if you have something in a clausal form, what's a generalization of a conjunction of clauses? Either you drop one clause completely, or you replace one clause with a single variable or something. I mean, you can drop clauses, that's generalization. Or you could drop individual literals from inside a clause, okay?
Right.
Because then you are taking conjunction of a bigger set, okay? Individual set. So as long as it is generalization and you apply the same criteria, you could still do it, okay?
Yeah, it will be
more work. Yeah,
it will be sound. But what I'm saying is that if your generalization leads to a huge formula, then that may not also be like that. I mean, yeah. But again, I think this is all some intuition in the sense that I'm not saying this because somebody has tried it and such.
Links to your questions. When you do ternary simulation, you only generalize cubes, is it?
Yeah, we generalize cubes to cubes, right?
Cubes to cubes. Oh, okay.
Yeah. I mean, I was trying to sort of motivate why we are like choosing to do this.
Yeah. I mean, it's interesting. I don't to see if this thing can be extended.
Yeah, definitely. Yeah, I think that will be an interesting exploration to do. Even if it does not lead to much optimization, at least knowing that that our intuition here is.
Yeah, there was some question by Paramalai someone.
Oh yeah, go on.
Yeah, are we following any specific algorithm for generalization?
No, this is just So go ahead, Diganta. Yeah.
Yeah, so there are probably a lot of different generalization methods that one can follow. So the one we are following is the one in this paper essentially, which is this. So I think they'll talk about this in somewhere here.
Yeah. So to
Down
make
here. So in
it
any case.
make it somewhat concrete, we decided that whatever that you do will at least be what is described in that paper. Now,
Yeah,
if you guys come up with some fantastic idea that you want to try, you're more than welcome to do it.
Yeah, definitely. Like if you think that this generalization can be improved, or if you have any great idea for generalization, even if it's not a great idea, if you have any idea and you want to try it, like I think that's a great idea.
Okay.
Yeah, but I mean, I'm just like mentioning, at least giving something that you can do, like even if you don't have any idea. Is that's what we are trying to do here. So yeah. So any other questions, or should I continue with the determinism?
Yeah, you can continue.
Yeah. Okay. So yeah. So this star is basically represents the things that can either be 0 or 1, and we are trying to. So these are the rules for the ternary simulation. And I mean, if you think about them for 1 second, it sort of makes sense that you can substitute star with 0 or 1, and these will still hold, right? So what we do is we already know that, okay, we have some fully expanded out t here, and we know that if we sort of apply the transition function to it, although transition relation is a relation, in some sense, if we substitute the t into this here, this particular t that we have, we get true, right? So what we do is we start replacing each one of these variables by star, right? So we replace x0 by star, and we substitute it into this, and we see that whether we still get true. And note that we will have to get true. It doesn't work if you get star, right? Because star would mean that you can potentially have 0 or 1 there. So you have to get true here. So we replace x0 with star, and we see if we get true. We replace, so if we do get true, we keep that, and then we go and move into x1. If we don't get true, we keep x0 as whatever it was, whatever actual literal value it had previously, right? So if we get a star here, we can drop x0 from our class. Otherwise, we'll keep it. So similarly, we move on to x1, and we replace the value of x1 that we had with star. So we had previously value 0. So we'll replace 0 with star, let's say. And we'll again evaluate this new expression internally and see whether we get true. If we do get true, then we can safely drop this x1 term from our cube. Otherwise, we'll have to keep it, right? And similarly, we do this thing. So one example could be something like this. So you try replacing x0's value with star, do the ternary simulation. It turns out to be true. So you drop x0, right? And then you try replacing x1's value with star, and it turns out that it doesn't come to true. So you cannot drop x1, but you now replace x2's value with star. And remember that now, since you have dropped x0, x0's value is always set to star, right? So x0 value remains a star, and you replace x2's value with star. And so when you do that, you sort of have 2 stars now, and you see that, okay, again, sorry, why did I write 1 here? So again, you see that you're coming out to be true. So you drop this x2, and then you go on to x3, and you see that if you replace with star, you don't come out to be true. So essentially, you find that you can sort of, you have a new ternary assignment for x0, x1, x2, and x3 that gives you true here. You not change the assignment of s, by the way. S is some fixed assignment, or some fixed fully expanded cube that you're working with. And what you have is this new sort of clause that you can, or new sort of ternary assignment for t that sort of still gives you true. So for some s, you have now replaced t, the assignment of the binary assignment of t, with this ternary assignment of t prime, so that t prime s, r of t prime s is now true, right? And remember, the way we are doing is sort of, we're going left to right, and we're replacing things by star every time and seeing that if whether that holds, whether we can make that stick or not. If so, we keep the star. Otherwise, we keep whatever previous value that we had, right? So this is, as you can imagine, this is actually fairly cheap, because all we're doing is we're doing some evaluations, right? I mean, yeah.
So when we are replacing x0 by star, what we actually do is we check for both x0 is equal to 0 and x0 is equal to 1. And check
that can be one way you can do that. But another way of doing it is to actually use these ternary rules. So the ternary rules are
define another value for
Yeah. So that can be another way of doing it. And I mean, I think both of this, I mean, you can sort of think about what you think would be more efficient in terms of writing code to do this. So that is, I'll leave it up to you. But yeah, both of these can be done.
Okay.
Yeah. I mean, okay. So just to complete the set of rules, star and star is star, star or star is star, not star is also star. I mean, yeah, obviously. So okay, so that this is what we do. So this is what they call the ternary simulation. What this will do is basically, once you get this full T, you would be actually able to replace a lot of your variables with stars and get a T. You get a smaller or ternary assignment T prime for this. Hello?
Yeah. I'm just saying, when you say smaller T, a T, that a cube that has smaller
number of terms.
Yeah.
So then you can, in terms of cubes, so you have your previous T. So with respect to the full binary assignment, your T was a cube with all your variables. Now with respect to this ternary assignment, you can just ignore all the variables with star assignments, right? So then you have a much smaller cube that you have to deal with. So then, instead of blocking,
Yeah. Okay.
Yeah. So as an example, you had your T was your, say, x0 and x1 and x2 bar and x3, and with respect to the binary assignment 1 0 0 1, and that goes to the ternary assignment star 0 star 1, which is the T prime assignment, and that corresponds to the cube. There is no x0, there is just x1 bar and x3, right? So now your T prime becomes x1 bar and x3. And what we do is, instead of blocking these T's, we block these T primes now, right? So this is basically one optimization that we can do via the ternary simulation. So that is this generalization of what we are blocking in this thing. Now notice that we can actually carry this forward, right? Once you block this T, so if you go back to this little pseudo code that I had written. So let's sort of improve this with ternary simulation in some sense now. So yeah, so again, what we'll do is we'll get the sat instance, and now before we do anything else, we'll do a turn. Okay, I don't know what that happened. Yeah, so we'll do the ternary simulation on this, right? So we get a T prime from ternary sim on T, right? And then into this Q, we add this T prime, right? Now, firstly, let's notice that this doesn't really, so this entire thing, by the way, is in a loop while Q not empty. Right, so it is in this loop. Now, firstly, let's notice this, that you can actually sort of so when you add this to this Q, it might happen in some later stage that when you extract a new S, this S is actually not a full cube with all your variables in there, but a partial cube, right? Because now your T prime is a partial cube and you're adding partial cubes. You might get an S that is a partial cube, right? And notice that all of this that we have talked about, that all of this will actually go through even if your S is not a full cube. So even if your S looks like something like, say, x1 and x3, then all of this will go through. So the same ternary simulation method will sort of work, because then when you're talking about the assignment with respect to X, you can reconstruct the assignment from a partial cube by putting star into all of the literals that are not here, right? So this will become star for x0, and then 1 for x1, star for x2, and then 1 for x3, right? So your assignment is now 1 star 1 star 1. So you can sort of extend all of these for your S's that are partial assignments or cubes with not all literals in them, and everything here will sort of go through for all of them. Stat checks obviously doesn't care, because for stat checks it's just a formula. And your ternary simulation, if you're working with assignments, then you can just assign them to star and it will work, right? Yeah. So now notice one thing, that we are doing this while we're sort of going over all the models from this particular S anyways, right? So when we usually do this while sat check, where we are, note that while CTA sat check has an implied thing here, is that we want to block out these assignments that we are doing every time, right? So essentially, whenever we want to iterate over all the models from a sat check, the way we do that is by blocking out those models from that sat check, right? So one way to do that is to always like, so okay, so essentially when we're blocking out this model from the sat check, we are essentially, I mean, one thing what thing that we can do is essentially, instead of blocking it from the sat check, we can directly block it from FI, right? So to change over to that mode, we just need to do some small refactoring to this code. Here, what we're doing is we're doing the sat check, and then we are blocking S, right? So essentially, this sat check gives us some T that goes to S, and then we block S, correct? So we can do this the other way around. What we can do is that, okay, we are going to assume that S is already blocked in FI plus 1. And remember that this sat check doesn't ever have any FI plus 1, right? So assuming that F is blocked in FI plus 1 doesn't change your sat check at all. And then whenever we get an assignment from this, we block it in, or T from this, we'll block it in FI, right? So changing that would basically mean that now in this thing, we sort of take this loop that we had, bring it down here, and we change this loop so that instead of talking about S, it talks about our T prime, correct? And let me just move this thing up. Okay, I think move this thing up, right? So this is, of course, under the assumption that all your S's that have been added to the queue. So now we are actually working with a different invariant here, is that all the S's that have been added to your queue has already been blocked from all the FIs, right?
So initially we are adding a state to the queue, right?
Yeah, initially you'll be adding a state. So that would basically be your this thing here. So you'll be, instead of calling remove CTI just like that, right? You'd be or you can think of it as that in your remove CTI, you originally at the top, before you go into the while queue not equal to empty loop, you're adding a state. Yeah, so that will be there. And since we have this invariant that everything that we'll add to queue needs to be blocked, so here you'll have to, before we add the state to queue, you'll have to block it in the FI plus 1. So remember this, that this remove CTA that we're calling at from not the recursive call here, because we don't have a recursive call anymore. The remove CTA that we are calling from the extend frontier is always going to have K, right? So it's not going to have any particular I here. It's always going to have K. So in some sense, we can, since it's always a K, we can sort of set K to be a global variable. I mean, just to make the pseudocode a little clearer. So we can say that K is some global K is just the number of frames that we have. And then what we do is we have this function is defined to, whatever it is defined to take in your state S. And what we do is that we just set FK to FK and not S. So we block S in the last frame that we added in, and then we just add S comma K to the queue, right? So this will be your thing. Is this clear?
Yeah. Okay.
Yeah. Yeah. So far this does sound, this seems sound and correct, right? Like this refactoring that we did shouldn't change the behavior of this function, or it shouldn't break things, right? Does anyone feel? Yeah. So now notice that we can actually do away with this while loop, and the reason why I'm saying this is that later on, the next sort of optimization that we'll see is it's going to be easier to see what it does when we don't have this other while loop here. So we can do away with this while loop, because whenever we are adding something, like whenever we are picking something from S, we are actually, going to iterate over all the models here anyway, right? So we have this outer while loop that is going to pick things from S and then do the sat check and so on. initial check and then sat check. And what this while loop is that this while loop continues over and over up until there are no more models in S or no more models of this CTA sat check, right? So okay, just give me one moment. I'm sorry. Turn off my phone. Yeah. So another way we can look at this. I'm sorry. Okay. So another way we can look at this is that this is something that is taking for this particular S, I pair. It is doing the CTA chat sat check for the S, I pair, and then it's going to add these things, and then it's going to block everything that it gets from the CTA sat check, and then it's going to do another CTA sat check for the S, I pair, and so on, right? But we can because we already have an outer while loop here, we can sort of rephrase this as doing this, right? So we say that instead of having a while here, we replace it with an if, right? And if there is a CTA sat check, if the CTA sat check passes, then we do all of this. If it or if it sort of gives an assignment, then we do all of this. And then what we do at the end is we also add this SI back into the queue, right? Now, if it fails, then we don't do this. So in this way, what we can do is we can replace the while loop with an if loop, right? Because for this particular SI pair, what was happening before is that for this particular SI pair, we come to this while loop and then we exhaust all the CTIs that we can get for this SI. Now what we're doing is we're doing something slightly different, but essentially still the same, which is that we're getting only one CTI for this SI. We're doing what we need to do for that CTI. And then we're adding this SI back into the queue so that eventually we'll get this SI back again. Correct? So is this refactoring also correct? Does anyone have any questions?
Yeah, this is but this is not a computationally inefficient, right?
Computationally inefficient?
No, I mean computationally same as the previous one, right?
Yeah. It will be computationally same.
Okay.
Because even in the previous one, for each things in your queue, you'll have to do as many things in the while loop anyways. And for this one also each things in your queue, you'll have to do as many things in the while loop anyways. So there is some popping from queue and pushing from queue, but if your queue supports peak operations, you can sort of work around that as well, right? Okay. So yeah, so you can peak SI from the queue, and then you can pop from queue or you can pop from the queue in an else clause and so on. So yeah, so this refactoring is, I mean, modulo the queue operations, this is computationally the same.
So the else part will be like popping S, right?
Yeah. So basically what I was saying is if your queue had some peak operations, then you could say that SI comes from peak of queue. So q dot peak, let's say. And then instead of pushing SI back into the queue, because you've peaked it, you don't need to push it back into the queue. All you need to do is in your else part, you just pop S, I from queue, right? So you'll have to figure out, depending on what exact queue implementation so on you use, you'll have to figure out what is a good way of doing this. But in any case, the added costs from the queue should not be too much compared to the rest of the costs, like compared to doing a SAT check, let's say, right? So for all intents and purposes, we can consider this, no matter what implementation of queue you have, we can consider this to be computationally equivalent to the previous refactoring, right? Does this answer your question? Hello?
Yes.
Okay. Yeah. Right. So this is one refactoring. Now with this refactored version, we can actually look at the next step of the optimization that we can do, right? So remember that now what we have is that we are, instead of removing one sort of like, instead of removing each one of these instead of blocking one CTI at a time, we are blocking multiple CTI at a time, right? Now, remember what happens is that each time we do this, we sort of, if you find a CTI that is hitting F0, we are sort of extracting a counter example. But if in the case that our properties actually, like our safety properties actually holds, then this will at some point will not get any CTIs anymore, right? So the question is, can we exploit that to somehow block more than just S? So S, remember, if you don't get a CTI, is not essentially a CTI, but can we somehow block more than just S, exploiting the fact that we haven't got a CTI, right? So to understand this, let's look at the situation where we haven't got a CTI, what that entails in terms of a SAT check, right? So S, remember, is going to be some Q, right? So it's going to be some, let's say, X1 and X3. And the SAT check, what that is going to do is that the CTI SAT check is going to be, there's going to be basically this is your SAT check, right? In the remove CTI that we had. If we are going to look for a state in Fi such that R of that state and S holds, and there is not of S and there is S prime that holds, right? So let's ignore the not of S for now, just for clarity's sake, and let's look at the SAT check, right? So it's going to be something like Fi and your R term, and you'll have the S. So S looks like X1 and X3 in our case. Or okay, let's just add in X1, X2, X3 just so that we have some clauses to work with here, some terms to work with here, sorry. X1, X2, X3. So and X1 and X2 and X3. Right? So now this is your SAT check that you're trying to do, and you're at a point where you don't get any CTIs, right? So what you know is that this entire formula is unsat, right? So essentially you're looking for, just to make things a little bit more clear, we are looking for Fi of T should hold, whatever that formula is, and R of T comma S should hold, whatever that formula is, right? So this we think we know that it is unsat. So there's no T that will satisfy this entire thing. So now what we can sort of try to understand or try to extract from this SAT check is that how many of these things were actually necessary for the SAT check to be unsat, right? So if your SAT solver gives you the information that from the clauses that you have added or the constraints that you've added, you can sort of think of this, and this as to be 5 constraints. From the constraints that you have added, only a few of them are actually necessary for your SAT check. That is, if you say drop your X2 constraint, your SAT check still remains unsat. Then what you know is that this new S prime, X1 and X3, right? This also represents states that are not reachable, correct? Yeah, because what this SAT check being unsat proves is that S is not reachable. So if your solver gives you that, okay, even if you didn't have X2 here, you'd still have been unsat, that proves that this X prime with X1 and X3 is unreachable, right? So what you can do then is you can essentially strengthen your frames with this X1 and X3, right? Because this is in any case states which are unreachable. So if you strengthen your frames with a set of states that is unreachable by ironing out a set of states that is unreachable, so you can, basically I'm saying that you can strengthen your frames greater than I. So if I plus j, you can strengthen all your Fi plus j for all j with and of not S prime, right? That will be correct, right? That will still maintain your frame, the invariance for your frame that we had previously, right? Yes or no? Or
Okay, yes, we don't worry about whether S prime holds that property or not because it's not reachable at all.
Yeah, because
okay.
Yeah, because if you have some, again, remember the idea is that we want to tie, like if you remember the propagate clauses and similarly this one as well, the idea is that we want to tighten the frames down a little so that hopefully some of them will become equal, right? So we can always tighten it down by S prime. So let's do that is basically what this algorithm is doing. Yeah, so you can add this not s in as another another clause inside your frames, right? So this is another optimization that we can do, and remember this is only valid if, or this optimization will only work if you have the information that your CTI sat check is unsat, right? So pictorially, what does this sort of look like? Similarly, you have your black and your red, and let's again have, let's say, 2 or 3 frames. So you have frame 1, you have frame 2, and you have frame 3, and say that you had found a CTI here and that you have blocked this. And then while trying to do the sat check, so remember that we are in our current state of refactoring, whenever we are working with some CTI, or whenever a queue has some CTI, that is always, we know that is always blocked. So we have blocked this CTI S that we had gotten. And now what we find is that, okay, this S, there is nothing in the previous frames that actually reaches this S, right? So then we have actually what this will give us, this unsat, what we can extract from the unsatness of this formula is actually some bigger S prime, right? So we can extract this slightly bigger S prime, which we also know to be unreachable. So what we're doing is we are not just blocking S now, but we are going to say that we are also going to block S prime, right?
That one will be T, right?
Huh?
That one will be T, right?
No, that one will not be T. So remember, we have not gotten a T. So if our CTIs, our sat check, actually, okay, let me just finish this blocking diagram and then I'll show in this diagram as well. So our sat check, if you remember, a CTI sat check is actually looking for a T here, such that this happens, correct?
And there, this is applied only when it is blocked.
Yeah, right. So only when we have proved S to be unreachable.
There is no T that is going into S.
Yeah. So our CTS sat check was looking for a T. So in a CTS sat check, in some sense, the T was the set of variables that we are doing the sat, that we can set in the sat check, right? And since it is unsat, what we have seen is that there is no T such that this happens, right? Does that make sense?
Yeah.
Does that clarify your question?
Yes.
Okay. Yeah. So this is not we're not talking about the T's here. We are talking about the S. And in fact, the way we're getting this S prime from the S is by getting the set of getting the set of assumptions that are, or dropping the set of assumptions here or constraints here coming from S that are unnecessary for this unsatness.
Yeah, and I think the advantage of kind of eliminating, so this is kind of eliminating more than what you need, okay?
Yeah.
But it is okay because in a sense, those things are not unreachable. So you'll keep on checking, okay? Potentially if you include them, you'll keep on checking and all of them will keep getting blocked at some point in the earlier frame. So unnecessary carrying along the backward trace, and then only to discover that it is blocked, okay? Therefore, those checks will be eliminated.
Yeah, so for example, you can imagine a situation where, say, you have a bunch of other points within this gray region, all of which actually go to this red region, but none of these points there is no T over here that goes to any of these points, right? So in your F3 here, there were 3-4 points that goes into the red region, but there was no point in F2 that ever got into any of these 3-4 points. So going from this S to S prime and blocking this entire S prime gets rid of all of these points for you in one step. Otherwise you'll keep getting these as CTIs anyways and so on. Right?
Yeah.
Like the procedure to get S prime will be like similar to the one in like reducing the size of cube in T, or will it be different?
No, no, this is unsat core. Okay, this is different.
This is going to be different. Yeah.
Yeah.
Okay.
So-
So,
so
we
this-
won't be substituting star and checking.
No.
No.
Okay.
No,
Yeah,
because here that would not be a very efficient thing to do. See, there the reason why substituting, I'll come to what we do here, but just to answer your question first, the reason why substituting star there worked was when you substitute star once there, you can actually, all you need to do to check for that, like all the work you need to do with that particular substitution is to just evaluate this RT and S, RT of S formula, right? RT comma S. And evaluating a formula is always going to be much easier than doing a SAT check over it, right? I mean, that
This
is,
is unsat check here. Okay.
yeah. Here, if you had to substitute star and do something like that, there you would have to substitute star and then again redo the unsat check, which is a lot of work that you're redoing, right? So there, that sort of a thing would look like, okay, let's drop x1 and see that do we still get unsat. Okay, we are getting sat, so let's keep x1 but drop x2 and see if we get unsat. And that is going to do a lot of many sat checks, and that is going to be very slow, right? So that's why we are going to not do that. Yeah.
Yeah, but and also here you will be using something called an unsat core.
Yeah, so I'll come to that. So
Okay, because I have not discussed that in the class. Okay, so this is extracted from a proof of unsat.
right, yeah.
So it will draw clauses here. Yeah.
Yeah, so I'll not go into the details of how exactly it is
You don't need to
extracted.
go into the details.
Yeah.
So I had promised them that I would discuss that because this time for some reason I've been no. In any case, so I usually cover resolution proof and the thing which I have not done this time. I could not do it, and yes, it is based on resolution proof. Okay, maybe I can just briefly show you. Okay, a resolution proof from that extraction of unsat core is fairly simple. I mean, conceptually simple. But these things are available as black box features.
In Z3 itself. So in Z3, in fact, there is a function that you can use which is called unsat core. I'll send you the link to the documentation. I'll not be able to do a code demo of that right now. I mean, I can, I guess, but yeah. So I'll talk about how you need to organize your code so that you're able to use that. But yeah. So
could we do like one more tutorial session
for unsat for this one?
For the set 3 part itself, like the code.
Sure. I mean, that is something. Okay, so fine. That is something very small. I'll see if I can do it right at the end of this if I have time. Otherwise, we can do another session as well. Sure.
Yeah. Was that your question, or was your question as to what function you invoke on Z3?
I think he wanted to.
Yeah, he did say about the function, but I thought like there would be like many functions.
No. This is just one small function. Okay, I'll show you the documentation for this. So what an unsat core is basically, so if you have, with Z3, for example, you add a bunch of constraints in, right? So you have your solver and you add, say your C1, C2, and so on up until CK, right? So what an unsat core is going to be is going to be, in some sense, a minimal set of these constraints.
Yeah, minimal subset. Okay. Yeah. Suppose this whole thing is unsat. What the unsat core gives you is a minimal subset. Even if it's not minimal, some subset. It may not be minimal. I mean, minimal computing may be sometimes hard. So it gives a subset of clauses in here, which still keeps it unsat. Okay, which still makes it unsat. So the unsatness is there are some clauses, they may not be germane to getting the making it unsat. Therefore, it will give a subset of those things, and then that's what is being done. So when it gives a subset, that subset, because it is eliminating certain clauses, will be a generalization of that S. Okay, that like Diganta pointed out.
Yeah. So that subset will basically give you the generalization of the S. So this is also called generalization. This is sort of another flavor or another place where we can do a generalization that we're doing, or that this paper does, and we are going to do as well. Yeah, so in general, in Z3, the way of doing it would be that you add these clauses in, and in this case, each one of these clauses is going to be the various. So you're going to probably add fi of t as a constraint, r of t comma s as a constraint, and then you're going to add x1, x2, x3, and so on as constraints, right? So then what you would do is, once you've added all of these as constraints, then you do a sat check. So that will be your s dot check and so on. And then if you see that this check is coming out to be unsat, then what you would do is essentially you would go for s. I think the thing is called s dot unsat core, as far as I remember. Right. So I'll open up the documentation for you guys so that you can just see. It's just this one thing. It will give you the list of constraints from here that are basically forms your unsat core, or that is the subset of the constraints that are necessary for you to get an unsat. So in the most optimal cases, that will be a minimal set. But as Sir said, that sometimes that may not be optimal. Like, it may not be very easy to find a minimal set, and solvers might return something that is not minimal, but it'll almost always be a subset. So yeah, so I'll open up the Z3 documentation here. Okay, I think I have it opened in the other set of things. Yeah, Nemesis settings. So right, so there we should have a solver somewhere, right? And yeah, there we go, unsat core. Yeah. So it returns a subset as an AST vector of the assumptions provided in the last check. So by AST vector, it means that it's going to provide a list of ASTs, right? So as you can see, can you see this, guys, or should I make it a little bit bigger?
I think it's okay.
Yeah, okay.
It's okay. Okay. I mean, I can go up to this, I think. Okay.
Yeah, I mean, as long as they can read, it's fine. I mean, I can't read, but that's okay.
Yeah, I okay.
My eyes are much older. Yeah.
Yeah, I mean, I'll make it a little bit bigger, but sometimes the page sort of
This is just fine, Diganta. Go ahead.
Yeah. So as you can see, it's adding some constraints. I think it is x greater than 0, y greater than x, y less than 1, and then y greater than -3. And then it is doing check of this, right? So now you get a code, which is an unsat code from this. So in a check, you can actually provide the what you need to want, what you want to check, and you can provide, in some sense, assumptions that are Z3 using to get their sense satisfied proofs, right? So essentially, when you usually with the procedure for you to check something using Z3 would be just add them as constraints, and then to just call check without any parameters, right? So what you need to do over here is something slightly different, which is that you want to guard each one of your constraints via a Boolean formula, right? So instead of adding in just the constraint x greater than 0, what they're adding in is that P1 implies x greater than 0. So P1 in some sense guards this x greater than 0 formula, right? So P2 is again guards this y greater than 0 formula, and P3 guards this. So P2 also guards the y less than 1 formula, and then P3 guards the y greater than -3 formula, right? So you have these set of 3 bools, P1, P2, and P3, that are being initialized here, and you're guarding all the constraints that you're adding into S via these Boolean formulas. And then when you call check, you give it a list of the Boolean formulas that you're guarding this thing with.
Keep. Okay.
Yeah.
You want to keep. Yeah.
Yeah. Essentially. So the constraints that you want to keep. So if you did not want to do a sat check over, say, this y greater than -3, if you did not want to keep this particular constraints, then you could have omitted this P3. Then you would have just added P1 and P2. Then, this constraint would still be in your solver, but because it's guarded by this P3 and P3 has no reason to be true, that would not affect anything in your sat check, essentially. Only P1 and only the things that are being guarded by P1 and P2 will be activated, because there the implies will be reduced inside the solver to your actual
Yeah,
constraints.
but there is a little bit of pre-planning that you'll have to do, no? Which means that you should be aware of which clauses you want to take the unsat core out of, okay? And then you
Right.
have to kind of
Guard them.
Guard.
And I'll come into that. So there is some like bit of pre-planning that needs to be done there, and there is some bit of methodical things that you'll have to keep track of. So that I'll discuss in some details a little bit later on. But in general, you'll have to keep track of what solver that you want to keep here, and you'll have to guard them. What constraints that you want to keep here, and you have to guard them when you add it to the solver. So here, for example, they have guarded this one with this. We've guarded both of these with P2. We've guarded this one with P3, and then it's going passing both P1, P2, and P3, right? And it says that it's unsat. And then it gets this core, which is called the unsat core, right? So as you can see, this is the assumptions provided to the last check. The assumptions are basically whatever you passed into check, and what it returns in this unsat core is a list of the ASTs for these assumptions, right? So basically, so essentially so this is saying something that what these assumptions can be in terms of syntax. From what I understand, you can actually pass in entire constraints here, but this is easier to do because then you're manipulating smaller ASTs when you're working with this code, right? So then what you can do is basically to check which of these constraints are in your unsat core. You can check whether P1 is in core, P2 is in core, or P3 is in core. So as you can see, this time Z3 returns that P1 and P2 is necessary for the unsat, but P3 is not, right? And that makes sense because X is greater than 0, Y is greater than X, and Y is less than 1 is itself an unsat thing, right? You don't need the Y is greater than -3. That you don't need this extra constraint for unsatisfiability. So only these two assumptions in some sense are necessary for your unsat. And so the unsat core contains only P1 and P2. So is this idea of unsat core clear? If you guys still want me to write some code and show this, I can do that maybe today or maybe later. But I think this sort of thing is basically demonstrates what you want to do. I'll talk about the sort of extra bookkeeping that you need to do to use this in a bit, but is the idea of the unsat core itself clear, and how you can extract S prime from that?
Yeah, it's clear.
Yeah, it's clear.
Okay. All right. So this, in this way, you can sort of extract S prime. So here again, what I'm going to do is write this in the pseudocode. So extract S prime from unsat core, and then we are going to block this. So remember that we are working with I, right? So we're going to block in F. So for all the future I's from Fi, so essentially we're going to run a loop for L in I to K. We are going to block FL with your FL is going to be set to FL and not S prime, right? So this is going to be your else part, right? So now let's come to this bookkeeping that you need to do to essentially do all of these sat checks in some efficient incremental way, and to do the propagate clauses properly, and to sort of keep track of like assumptions that you're adding in for the unsat check and so on. So for that, I'll go on to the next page, and so essentially, first things first, you'll have to keep track of the number, all the clauses you've added in to each frame, right? So essentially, whenever you add in a clause to a frame, so remember that when you're doing this propagate clauses over here, right, you'll have to iterate over all the clauses in your frame, right? And you can actually query the AST that you have added into Z3 and propagate over that, or query your solver and get iterate that way. But that is going to be really slow because you're going to have to, parse ASTs used by Z3, and you don't want to do that in Python code. So essentially, I'd say that a much better thing to do is to maintain external lists of clauses that you have added in for each one of these FIs. And you maintain this list of clauses not as Z3 expressions. I'd say that maybe maintaining this as say lists of variables or lists of assignments even might be a great idea, right? And then whenever you want to do a SAT check, you convert them to Z3 expressions. So, or you can keep them as Z3 expressions and as a list of things. But I'd say that don't keep them as just Z3 expressions, because then if you need to iterate over the terms in your clause, then you'll have to again go into the AST level, right? So for each clause, basically for each frame, you want to keep a list of clauses, and for each clause, you want to keep at least a list of variables with the particular, with their negation flags in a list somehow. And additionally, you can also keep the Z3 expression for that clause cached in. That's up to you. Yeah. So this is one bookkeeping that you'll have to do. So essentially, whenever in the pseudocode, I say, I'm basically blocking a clause or doing anything like that, you'll have to always make sure that you over there itself, you also add this to your list, right? So of course, the good way of doing it too is to probably define a frame class and then have a method for blocking, which handles this, encapsulates this for you. I mean, at least that's how I would say I would do it. It's up to you how exactly you would want to organize this. Now, so that's one of the bookkeepings that you want to do. It's that keep list of clauses and add to that list whenever you block. Right. So the other thing is that notice that one of the primary things that we do here is just blocking clauses, right? And one of the things that we would want to avoid is that if a frame has a lot of redundant clauses blocked into them, right? So in fact, this itself can happen a number of times, is that when you're adding in a clause for blocking, your frame might have, so you're adding, say, not T prime in there, your frame might actually have that same not T prime in there, right? So whenever you're blocking a clause, you want to do a check as to whether that actually removes any points from your frame or not, right? So to do that, you would want to basically, so whenever you want to block a clause, you would want to check whether that is actually a redundant operation or not.
No. You mean subsumption checking here?
Yeah.
Yeah, okay. So whether the clause is actually present or it is included in some other clause.
Yeah. So there'll be two levels of this subsumption checking.
Yeah.
One is
there is one thing. See, there's one thing that I do. I mean, do you really need to check? To see if it is already present? Because if you use generalization, maybe you will have to need that. Okay.
Yeah.
Correct. See, otherwise, okay, as a side point I'm making, okay, since if you don't use generalization, then all you're doing is either whatever clause that you strengthen in the blocking phase, you kind of add it to all the way down, okay, up to 1. And similarly, in the propagating phase, whatever that is relatively inductive, from that point on, all the way up to the latest thing, you will propagate. Okay, so it's the same clauses that are being propagated and so on. So the checking of equivalence. So these things already, the fact that they are included. If they're monotonic, is actually monotonic not only in a logical sense but also in a structural sense. In the sense those clauses Fi, the set of clauses in Fi are Fi is a subset of Fi plus 1 is a subset of Fi, correct? Okay. Yes, because Fi plus 1 is superset, is weaker. So Fi plus 1 is a subset of Fi. Now, so even the checking of and even there's a further thing. All the clauses without generalization, they're either clauses that belong to the property, okay, formula expressing the property, or they are just cubes, negations of cubes. Now, when you generalize, then it becomes something different. So there may be, because the subsumption checking could be done syntactically, but maybe it won't work if you do generalization. You will have to really check if it is included if it is included in one of the clauses. Correct? Yeah.
Yeah. I think we cannot avoid that if we do generalization.
Yes. Yeah. Okay.
So yeah. So this is one cost in some sense that we are incurring when we're doing generalization, but at least according to the paper, it is worth it in some sense. So yeah, whenever you add a clause, you want to do a subsumption check. So before you do a subsumption check, you actually should check whether that clause is in the list or not. So check. So let's say the clause is C. So check A. Is C in list for Fi? Because if it is, you can just return early. Otherwise, do a subsumption check, right? So do check for. So this is a SAT check for. Basically, do a validity check for this formula. The formula being that Fi implies C. Right? And in general, subsumption checks are not very expensive because these are SAT checks where you sort of add in a lot of singleton clauses, and most SAT checkers do well with a lot of singleton clauses. They can easily derive a lot of things from there and make fast and come to fast conclusions from that. But yeah, in general, you need to do that to prevent having a lot of redundant clauses in there. I think is a really cheap and really important optimization that you can do. Both of these are, in technically speaking, optimizations. But yeah, I'd say both of them do both of them. You can, I think, maybe experiment and try and see, compare what happens if you do or don't do B, right? So this is a question mark. But I'd say that at least write the code for implementing B, because it's not going to be in terms of code much, right? So write the code for implementing B. And then you can decide after doing some tests on some examples as to whether it is worth it or not. But according to the paper does that, and according to the paper, they say that this A case actually catches a lot of cases itself, but sometimes things do slip through the cracks and they do end up coming to B. And in those cases, B actually kicks in. So it's not like B never is used, but it is used sometimes. But the paper is also not very conclusive as to whether B is useful or not, though they keep it in the code. So I'd say that maybe you can, have a configuration or a switch somewhere that you can switch on or off this B check, and you can check and see whether there is any difference of performance you can notice with B, with or without having B, right? So these are the two basic things that you need to do in terms of bookkeeping first and foremost. Now, the next thing that I want to talk about, it is some bookkeeping thing, is I want to talk about how you can do these SAT checks incrementally. See, whenever you do a CTI check that involves some frame Fi, you're actually going to derive a lot of different things for that particular frame. Like the solver is going to learn a lot of different new clauses for that frame. And whenever you do a next SAT check for the same frame, or a next CTI check for the same frame, you want and keep those particular things around, right? So you want to keep those particular clauses or the learned things around in the solver. So you want to do the solving incrementally, right? So now one way to do this in Z3, or basically the only way to do this in Z3 is to use the same solver instance, right? So in Z3, each solver instance sort of carries around its own set of learned clauses. And whenever you do a subsequent SAT check, if you don't do any push pop, if you don't pop out the clauses, then whenever you do a subsequent SAT check, those new learned clauses are still present and used for that new SAT check, right? So in that sense, Z3 is an incremental solver, and that has huge performance benefits. So you want to use this feature. But here you have different frames, and for each frame, you would have a different set of, so for example, you have 3 frames, and here for each of these 3 frames, you would have a different set of learned clauses, right? So one way which I was thinking initially is what I was thinking is this way is what I would present, but I actually think that there is a better way to do this. Is to keep one solver for each frame, right? So that is one way. So you keep one solver for each frame, and each solver has its own set of clauses that it keeps track for that particular frame. And then you have S1 for F1, keeping track of learned clauses for F1, S2 for F2 keeping track of learn clauses for F2, S3 for F3 keeping track of learn clauses for F3, and so on. So that is one way of doing it. But what we are going to do is we are going to actually use a single solver, one solver, and that is what the paper does as well. And the way we are going to do this is basically to use this particular idea that there was. So if you remember here, we had this idea, right? We can guard the clauses that we are adding in via some Boolean variables, right? So we'll reserve a set of particular variables. Let's call them F act, or okay, so F act I variables. So these are basically frame activation variables. So we have one such F act for each frame. So for each Fi, we have one F act I variable, right? And then whenever we add a clause that is relevant for a particular frame, right? So say whenever we want to add a clause to a frame, so say we have a clause C and we want to add it to Fi. So we want to say that Fi is going to be set to C and Fi. Then what we do is, instead of adding C, we add F act I implies C to Fi, right? So if you remember this implication in, so again, we are actually like internally everything is going to be represented in CNF. Even if you pass this to Z3, internally everything is going to be represented in CNF. So if you remember this implication, how it is expanded is that you either say not of F act I, or you say F act I and C, right? And then if you have, say,
this is just not a fact I or C, that's all.
Yeah, okay. Not a fact I or C,
Or
right?
C.
Yeah. So then if you say, if you add in fact I over here, then if you add in the fact I, then this thing will be expanded. Like this not a fact I part will basically die off, and you'll get the C and Fi part, right? So what this paper does is actually they do something slightly different in some sense, is that instead of adding this F act I implies C, what they do is they add in this as a thing. So they'll add not F act I and C and Fi, right? So this way, if you have your F act I as, if you have, say, if you, when you're doing a SAT check with respect to Fi, if you add in F act I as another assumption, then sorry, okay, I think, yeah, wait, so if you add in F act I and this, they will sort of cancel each other out, right? So in some sense, this will become false. So yeah, okay, I think, sorry, so yeah, so I'm sorry, I got a little confused there myself. So yeah, essentially what you need to do is basically add this not F act I or C, and then you want to end it with Fi. Eternally, this will get converted into CNFs, and so you essentially what you're doing is you're guarding it via the implication. And you can actually not worry about converting this to CNF yourself. All you need to do is basically guard everything that you add in Fi via this implication in terms of F act I.
So then
Yeah.
you have to introduce this new literal
Yeah.
with a new variable every time you do strengthening, either in the backward or the forward phase, no?
Yeah, you'll have to introduce this new variable and implication.
And then when you actually call these do SAT checks and unsat checks, etc., you will have to do it with by turning on
This variable. Yeah.
these variables appropriately when you're depending upon which frame you're doing.
Right, exactly. So for example, the SAT check for the Fi, this CTI check for Fi, right? So the CTI check for Fi, as we saw over here, this is basically what you would want to do. So you,
Diganta.
Yeah.
So it's 2 hours since.
Oh, okay, yeah.
Okay.
So I think I'll have to quickly wrap up.
Yeah, I think you have to wrap up in 5 minutes. Okay.
Yeah.
I mean, logically, of course, it's there. It's there. You know, it's a Sunday, and you know, I mean.
Yeah, let's not destroy the Sunday evenings for them. Yeah.
You don't have anything better to do either.
At least you have to go get some tea. I mean, I just.
Yeah.
No. Okay, so why don't you, take 5-10 minutes, and then if they will, if they are, enjoying it, you continue. So I'll have to go get some tea. Okay, so
Okay,
you
sure.
continue. So I'll be back in 5 minutes. Okay.
Yeah, sure. So I mean, I'm fine with continuing myself. So I need to hear from Amin as well. So
Yeah, then
when
we
I say
need
that,
to have, there is a logical point, and if you guys want to continue for, to kind of do it, then continue, please. And,
Yeah, like for me, it would be
then we'll
better
do
to
it.
stop at 5:30. I
So,
think.
and then
yeah,
you,
I can't.
I'll be back. Okay.
Yeah, sure. Yeah.
Time. I'll have to end it. So anyway, so you're about 15 minutes out. Yeah. So whenever it's logical. Yeah.
Yeah. So Amin, can you tell me what you said? Repeat once.
Like if it's 10-15 minutes, then I'm okay. But
Right.
like
Okay.
if it's going to
So
take
so
longer,
I'm going
then
to request you to do something like 5 minutes later. Just remind me, because I don't have a clock in front of me right now. I'm really sorry about that, because I turned off my
yeah,
phone.
sure.
Yeah. And this my system clock is being hidden by Zoom right now, this Zoom tab thing. So yeah, so just remind me in 5 minutes, right? I'll try to wrap up very fast. So what you need to do for this block part, whenever you block, is this: whenever you add a clause. Okay, so maybe I don't need to write it as in point number 3 here again. What you do is you do a valid check, or before you do a valid check, what you firstly do is, I think even before all of this, what you do is you recognize that Z3 EXPR for C will be F act I implies C, right? So always remember to guard this with F act I, because if you ever forget to do this, there'll be a huge, it'll be really difficult to debug that. I'm just warning you. So do not forget this, and wrap all of these into classes, and have everyone look at those classes, just make sure that they have not forgotten this. And similarly, when you do any SAT check, so for example, the SAT check for the this part here, right? So there you'll have to basically, so you're adding this fi of t here, right? So what you'll do is basically you'll add this as a constraint. So before you do the SAT check, you in your solver, you already have this fit added in as a constraint, right? Because whenever you're adding these things in, your Z3 expression of this is this, and when you add this to thing, what you do is you take your global solver and you add this constraint in, right? Fact I implies C, right? So whenever you add this constraint in, remember that if your previous fi look like fact I implies C1, and now you have added in fact I implies C2, then whenever you set fact I, these two things will together, so these are two constraints that are being added together. These two things will together resolve to C1 and C2, right? So whenever you add in, so you're basically, by doing this, you're setting your solver to a state so that whenever you add in fact I as another constraint, then your solver will now have fi added in as a constraint. So is that clear?
Yeah. So
Yeah.
how do we check fi implies C here, the B1?
Yeah. So for that, what you'll have to do is essentially, so for any SAT check, essentially what you'll have to do is, when you call this check, if you remember in the doc, you can actually pass in this Boolean variables, right? So whenever you call this check and you want to check for fi, what you'll have to do is you'll have to call it with the Boolean variable. The rest of this is exactly the same, right? So you'll basically say that inside your thing, you'll go s.check. You'll pass in this fact I. So when you pass in this fact I to s.check, immediately the state of the solver becomes such that your the solver will now have fi as a constraint. So note that since this is being passed as an assumption, this solver, the fact that the solver will have fi as a constraint will not be kept around after the check term, like the check function returns. And the other thing that you can pass into check as another assumption is C, right? I mean, sorry, not C, right? And if this is unset, then you know that this thing is valid. Otherwise, you know that, like, if it is unset and this thing is valid, then you know that this is subsumed, so you don't need to add not C. Otherwise, you will have to add not C. add C, right?
Okay.
Yeah, so you can add this not C into a constraint. So another thing that you can do is you can, s dot push, s dot add, f acti, and these two things are equivalent if you think about it. F acti implies not C, and then you in your check you don't have the not C passed in, right? And then once you've done the check, then you do s dot pop again. So this is another way you can do this. So both of these are equivalent. This, or you can just do s dot check f acti and not C, right? Is this clear?
Yeah.
So yeah.
We do the bookkeeping, so just to make sure that we for the age check mainly to
For
check
the-
for duplicates, right?
Yeah, we'll have to do all of this to check for duplicate clauses. But the reason I'm asking you to, so the reason,
we did some bookkeeping, right? Instead of storing it as fully Z3 for. Okay,
Yeah,
that's
yeah,
not
yeah,
for
we'll
parsing the classes. Okay.
yeah. It's, if you want to avoid the parse in the clause, we'll have to keep this list of FIs, right?
Okay.
And again, when I'm saying s dot add here, there is another D step, which is to add C to list, so you'll have to figure out how exactly you want to store this list. That's not very difficult. I mean, I just say that keep it as a list of pair of Boolean and literal variable and something like that. Okay. Yeah. So that you can, that's fine. That you'll have to do. It is bookkeeping that you have to keep track of. It's not very difficult to come up with a good way of doing it. So you can figure that out, and is what I'm claiming. If not, then you can always ask. I'll be there. Yeah. So is this clear for up until now? I just want to mention one last bit of optimization that we can do, and then I'm going to stop.
Okay.
Is it clear?
Yeah.
Up until now? Yeah. So yeah, so up until now, if everything is clear, that all the bookkeeping and all this this adding of effecti as a guard to all of these clauses is clear, then I want to mention something that we were doing. So this is what your CTI sat check was. I'll write this CTI sat check here. So this is optimization number 3 in some sense. So CTI sat check was initially going to have R of remember T is the free variables in some sense, right? Because the S variables are going to be contained by this. So our CTI sat check was essentially having this as our sat check, right? So R of S and T and Fi, and S is, if S is equal to X1 and X2 and so on, then you have X1 and X2 and so on, right? So okay, I mean, technically the variables in S are also free, and you'll have to make sure that the variables in T and variables in S are different. But that is fine, because I mean, these variables will immediately get reduced out because you're already ending it in some sense, right? So now the way you can so the way to extract the unsat clause from here would be to basically, when you're doing a check, I'd say just do this s dot check, put in the entire R clause over here, which you'll have to basically generate because you're going to substitute different variables and so on over here, right? And then or you can keep a cached Z3 expression of the R clause, so you can figure that out as well. If not, again, I'll help you out. And then you have Fi, and then you have X1, X2, and so on, right? And then if you do Z dot, so if this check actually returns unsat, then you can do Z dot unsat, S dot unsat code. And that will give you the list of, it'll give you a list of many things. It'll most likely it'll contain R and Fi always, but it'll always, it may or may not contain all of your exercise, right? So you see which exercise it contains, and if it does not contain an exercise, you can drop that and get S prime that way. So this is also clear, right? Yes, no, quickly.
Yeah.
Amin as well, right? Being kind of quiet.
Yes.
Okay. Yeah, and also please do remind me, how much time do I have?
It's already 3 minutes extra. 5:33.
Okay.
Yeah.
Okay, so I'll quickly just, okay, up to you. I mean, tell me.
No, like Yeah, please continue.
I mean,
Like
no,
I would prefer to have like a full session with like maybe when we start the implementation, because
sure. Okay, you know
we
what? That
would
is
have
actually,
like a lot
I think
of
that
doubts.
that's better, no?
yeah, that is better. That is better.
So
Yeah,
they will have time to digest this thing, and then
Yeah,
I'm sure that you'll need a follow up.
right. Yeah. That is actually.
Yeah, I think we need we need one more tutorial session.
Sure.
Something like this.
So I mean, since it's already been some time, so I wanted to say this like another small optimization that one can do, but I think I'll leave this for the next session. What do you think, sir?
Yeah, I think so. Yes.
Yeah. It's been a long while. I think let's
Correct.
let you guys think about this. Yeah.